Welcome, I am Damien Zufferey and I will present our work on using multi-party session type to implement and verify robotic systems. This is joint work with Rupak Majumdar and Nobuko Yoshida. Let us first look at an example. This is one case study we did to test our approach. We have a few robots cooperating to sort objects by color. The small card carries an object which is either red or green. First, the card moves toward a camera to identify the object's color. If the object is red, the card moves to the left side, where a robotic arm picks up the object and puts it into a bin. For green objects, the card goes to the right. Then the card returns to initial position to receive a new object. Because we only had 2 robotic arms, we place the new object on the card manually. In this work, we are interested in statically verifying that a robotic choreography executes correctly. This means we have to deal with multiple aspects of cyber-physical systems. There is some computation to decide what to do, communication to coordinate the different actions, and to interact with the physical world, control is required. By execute correctly, we mean that the communication happens without problems such as deadlock. For the robot's motion, we also check properties such as the absence of collisions. Let us look back at our running example. The coordination involves 5 robots. During the run, they exchange 16 messages and execute 53 motion primitives. The motion primitives are basic control actions such as moving to a position or grabbing an object. For the verification, we start with a global specification of what the robot should do. The simple approach would be to check all the behaviors using a product constructions. However, as the number of robots grows linearly, the state space gets exponentially larger. Therefore, we need a different approach. To avoid taking a product, we combine 2 approaches: multi-party session types and assume guarantee reasoning. Multi-party sessions give us a top-down decomposition, starting with the global specification, extracting local specification for each robot, and checking that the local specifications are implemented correctly. Multi-party sessions' main focus is the communication. For the motion, we use assume guarantee reasoning. Assume guarantee reasoning works better in a bottom-up fashion, starting with the individual behaviors and composing them. Before we discuss these 2 parts in more details, let us introduce our model. On the software side, we assume point-to-point synchronous communication and zero-time computation. Concretely, this means that we are looking at systems where the dynamics are relatively slow compared to the computation and the network. The robots are modeled as dynamical systems with an internal state, external inputs to represent the influence of the environment, and to check for collisions, each robot comes with the space it needs to move. This footprint is a function of the internal state. Let us now present the motion primitives and assume guarantee reasoning. In this work, we look at the motion primitives as contract. We only use their specification. Their verification is an orthogonal question, and there are techniques to verify control code. Motion primitives are 7 tuples. This can look a bit scary, so let us explain each element. On the picture, we see a trajectory, a curve over the internal state and external input. Time flows from left to right. The bottom plane is the internal state, the back plane represents an external input. The precondition is what the state and the external inputs should be at the beginning of the motion. The assumption is what the robot expects about the external input for the duration of the motion. The guarantees is what the robot does with its own state. The postcondition specifies the state and inputs at the end of the motion. The footprint, which is not shown in the picture, over-approximates the robot's resources. The duration gives a lower and an upper bound on how long the motion lasts. Finally, a motion can be interruptible or not. This bridges the message passing layer and motion. An interruptible motion finishes when a message comes. An uninterruptible motion finishes on its own. We start with motion primitive for single robots and recompose them when multiple robots execute motions at the same time. Here we show the case of two robots. The composition checks a few things. First, the assumptions and the guarantees of each system really mirror each other. Second, the durations need to be compatible. If one process sends at the end, then the duration needs to fall within the other's duration. If both receive, we need to be able to find an interval where reception is possible for both. Finally, we check that the footprints are disjoint. This presentation is simplified. To be really compositional, the composition of two motion primitives should be a motion primitive as well. In the paper, we give an assumed guarantee rule that does exactly that by generalizing the ideas I just explained. Now that we have seen all motion primitives compose, we can look at the coordination layer. The motion session calculus brings together message passing synchronization and motion primitives. In this picture, we see the syntax to write a global specification. Let me guide you through the main elements. At the top level, choreographies are big while loops. This is not a fundamental restriction, but it makes it easier to check that a choreography is well formed. Then we have sequential composition and a separating conjunction. By default, a choreography specifies actions occurring in parallel. The separating conjunction forces two subparts to be fully independent. We use this information to speed up the verification. The choice is tied to the communication, as is the case in multi-party session types. The difference to normal multi-party session types is that we have guarded choice, and the values sent in messages must respect some properties. This is needed to reason about motions and communication together. For example, if a robot sends to another robot a location where they should meet, we need that the chosen location can be reached by both robots. Finally, we have motions. Here's the choreography for the sorting example, represented visually as an high-level message sequence chart. It has been simplified to fit the slide. On the left, you can see the overall structures, a big while loop with two branches. The choice between the two branches depends on the object's color. On the right, we show the details of the part up to the choice and one of the branches. We can observe that the messages signal transition between phases in the choreography. Messages also mark the transition between joint and separated actions. This is visually shown as the distance between the process timelines. Once we have a choreography, we project it to obtain local specification. The projection has a few steps. First, we need to check that the choreography is well formed. The separation forms a partition of the processes, the messages and communication work together. This check looks at the duration and interruptibility of motions. A well-formed choreography can be projected. The projection itself just keeps the action of a specific process. But we have to be careful. The projection can introduce new behaviors. An operator called merge checks that the projection does not introduce any unwanted non-determinism. Merging checks that the messages carry enough information to disambiguate choices. Let us look at the rightmost process in the example. The first process makes the choice, then the second process forwards that choice, and this is fine. On the other hand, if the second process does not properly forward the choice outcome, then the third process can get confused. What makes our merge operator interesting is that we have time systems. With time, not receiving any messages also carries information. After the projection, the final step checks that the implementation follows the specification. We use subtyping to bridge the specification and the implementation. In the illustration, we saw the local type on the left, a subtype in the middle, and corresponding to the subtype on the right. In the case of internal choice, choice followed by sending, a process is free to take a subset of the alternatives. For external choice, choice followed by receiving. The implementation has to provide at least the specified alternatives. For motions, the subtypes correspond to refinement. This means that what is expected, the precondition and assumptions, can be weakened, dually what is provided, the post-condition guarantees, can be strengthened. For the duration, it depends on whether the motion is interruptible. For an interruptible motion, the duration interval needs to be larger. Concretely, the robot is ready to receive earlier and can hold its position for longer. For an uninterruptible one, the duration interval needs to be smaller. We evaluate our method on a few case studies. The main one is the sorting example. In terms of effort, the most time-consuming task is writing the specification of the motion primitives. The upper table gives the line of code for the specification of each robot. The Moveo arm is the one seen on the left, and the Panda arm is the one on the right. The programs themselves are not too large, about 30 lines of code for each robot. The lower table shows the size of the choreography, that is the global type. Then the specification is split into 3 parts. The syntactic check is the part of the projection which does not involve assumed guarantee reasoning. The compatibility checks includes the assumed guarantee reasoning. This part dominates the verification time. Finally, the typing checks that the code match the local specifications. The other example we use comes from our earlier work. The gist is that we can now have more detailed specifications, so it takes a bit more effort to write, but it is much simpler to verify. The introduction of the separation in the calculus accounts for most of the changes. Our implementation has been evaluated and is available as an artifact. You're welcome to try it. The implementation is in Python and comes with a runtime and a verification backend. The artifact evaluation is only about the verification backend. For the runtime, we use ROS, also known as the Robotic Operating System, as a message passing layer. For the verification, we reduce the assumed guarantee reasoning to SMT queries, and we use dwheel4 as the backend solver. In the course of this project, we make it a point to work with wheel robots. In this slide, you can see the 5 experiments we have in the paper. Our goal is to be interdisciplinary and understand the challenges of robotics. However, because this is a very large field, we cannot tackle everything at once. In this work, the focus is using communication to decompose the verification problem into smaller subtasks. In other works, we are also looking at how motion primitives are implemented and verified. Having experiment on actual hardware is needed to understand one model to use and the assumptions we can make. For instance, we use synchronous communication, even though it is technically not true. But in practice, this is good enough for our setting. With synchronous communication, we can integrate subtyping to our approach. Subtyping is much harder with asynchronous communication. Stronger models give us stronger results, but it limits the applicability. In the end, it's about understanding trade-offs. Thank you for staying until the end of this presentation. We covered the main ideas, but only at an high level, so I encourage you to read the paper for the details. If you have any questions, don't hesitate to reach out to us. Goodbye.